3 months, and 400 million visitors come to this place. And yes, that's more than the entire population of United States. Now, before I get into sampling and tracing, let's do a little bit history of the observability. So we started with the basic network monitoring with SNMP. We get at the hardware status and like CPU, uptime, and memory. And admins can do the network polling and get an alert if it crosses the threshold. Then we move beyond the hardwares to services and servers. Now we have host check and services check. Now we have dashboards which has red or green signals. So now we know that if something went wrong, then we get these signals. Next, we went to monitoring. We get, instead of the red or green signals, we have dashboards and better insights into it. Next, now observability become a thing, and people know about logs, metrics, and traces. We have a unified observability platform with all these three things. Metrics told us what is happening. Logs told us when it is happening. And traces help us where it is happening. After that, we expanded the 3 pillars into 6 pillars. We added profiling, real user monitoring, and synthetic testing. This helps us to get the end-to-end visibility, user monitoring experience, and this is now a proactive testing. Now, today we are with AI-powered. All these things that human might have missed now can be captured with the artificial intelligence. OpenTelemetry made a standardization way to collect the data. But let's be honest, with all these technology, all I want is to bring my application up as soon as possible. Fast incident response is what matters to our users and to our business. The true value of observability is to identify the problem, a quick problem identification, which is finding the needle in the haystack. All I want is to minimize the mean time to resolution. Now, let me share with you my usual debugging flow with the tool SigLens. So it all starts by getting an alert that something went wrong. It could be a customer complaint, monitoring alert, or an error notification. Now the clock starts ticking, and we need to fix the problem as soon as possible. Next, I will look at the matrix for any anomalies. This will help me to identify an affected service. I will look for a certain spike, drop, or a pattern change. Matrix help me to find where, but not why. Next, we look to the relevant traces. So we now have the service name. We will look for the traces which have that service during the time of error. Traces give us a full visibility of where the things are happening and which is the root cause. For a deeper analysis, I move to the red matrix. Rate is the request, how many requests are happening. Error told me if something is wrong and how often it is happening. Duration is how long it is taking. So during this whole process, you can see that tracing provides the highest fidelity signal. It provides a complete visibility into the entire request path across all the services. Now you have a complete picture of what is happening inside your system. It connects all the dots between the services and the components. Now let me tell you how debugging becomes so easy when you have good traces data. So as you can see in the center, you have a graph, which is duration over time. And all these dots are trace requests. So you can clearly see some of them are red dots and other are purple. So now you can see the red denotes the error traces. So it's easy to find that something is wrong in the system. And there are difference in the size. So the one which are taking longer duration will be a larger size than the others. So high duration traces make the debugging easy. You can see the clear pattern. You can see that consistent failure happening point, and it will lead you to the direct root cause. Even better are the error traces. You can easily find which line number is the error happening. You see the complete stack trace available to you, and you can immediately take action instead of finding or spending hours into finding the problem. Now you can fix the problem in minutes. Here comes the problem. What if all the traces are happy and successful? Your customers are filing complaint. You see there is some problem in matrix, but your traces says everything is fine and happy. This disconnects creates a troubleshooting nightmare for a developer to find the problem. How can you solve a problem if you can't see that problem? So what is the mystery behind these happy traces? So yeah, it's sampling problem. Now let me explain you how this sampling leads to this mystery of happy traces. So this is like you have all the traces, and we are collecting 10 million traces per hour, out of which 0.5 are the error traces, which are shown with the red dots. And these red dots you need to find and fix the problem. But due to the huge volume, most of the systems do 1%, typical 1% rate of sampling, which is collecting one trace out of every 100 trace. Now we get our results, the sample trace. Now we have 100,000 traces per hour. But did you see that we don't have any error traces? So random sampling is difficult for us to debug the issue because it missed all the important error traces. So we lost the needle in the haystack while throwing most of the hay. So why do we do this in the first place? Too much volume. So we have a huge amount of volume for the traces, which most of the systems can't handle, so we do sampling. So you would say, like, why not do tail sampling, right? Keep only the interesting traces, like the important ones, the error ones, and the slow traces. But today, most of the vendors don't support it. And those who do that are like premium pricing tier, or they have some limitations. Let me explain you why it is hard to do the trail sampling. So first is that you need to collect all the spans until the request complete, because you need to have the complete picture of the trace before you move forward. Sorry. Second, you need to, today, in the real-world scenario, this means service needs to be coordinating between different clouds and data structures. This leads to a huge volume systems and leads to a lot of cost for the storage. Fourth, all these processing overheads makes impact in the application performance. Let's picture this with some numbers, how the trace data can be big. So let's say you have 10 billion transactions per day going, which means you have 10 billion traces, as each transaction is a trace request flowing. Typically, a trace has 300 traces spans. Each span represents an operation in the service. And each span has some metadata like timestamp, tags, header, which adds up to 2 KB. So now you can see you have 3 trillion spans happening per day, which combines to 6 petabyte of data. In the term of storage, you can see 1 terabyte of SSDs, 6,000 SSDs will need daily. If you convert, it will be 60 complete servers. And even in the cloud version, it will cost you a fortune to save this data daily. And I'm not even talking about like querying this data or searching about. Sounds impossible, right? Now with this huge volume of data, how can we fix this problem? So let me show you some techniques that we can use to get this 100% sampling. First, use columnar database instead of traditional row-based database. So row-based storage, we store all the fields in a single record together, while in columnar storage, we store all the values of a single column together. So this is critical because same type of data makes a good compression ratio. So doing this change will at least give you 10 to 20x better compression rate. Next, we can use different type of algorithms for different type of column types. Let's say for timestamp, we use delta encoding. Instead of saving the absolute value, we store the difference between the timestamp. For strings like service name, operation name, we use dictionary. For IDs and numbers, we use bit pattern. This will give you another 2 to 3x better compression. Next, we can use probabilistic filters like Bloom filter to increase your query performance. It will give you a faster check if a trace ID exists or not. This also saves up the space and treated like a indexing, which can be done with less space. Partitioning is crucial. We can do it on the base of timestamp or also for the trace ID. So it helps with the storage and the query performance both. So for the timestamp, we do the partitioning based on the timestamp, so the recent data can be accessible quickly. And for trace, we do the division based on the trace ID, so all the spans belonging to a trace ID could be in the same shard. This also helps in parallel processing and increasing the query performance. Next, we can have a better data structure. We can divide our tables into different type of tables, which will help us, again, in the query performance. Let me talk more in the next slide. So it will help you in efficient lookup flows. So you have a trace ID table, which will have minimal metadata like timestamp. Then you have association table, which will be a map for trace ID to span ID. And then you have span table, which has all the details of a span. Now, the key innovation here is the special shards for error and slow spans. So you store error and the slow spans in a special storage. So it is accessible faster, and you don't have to go through all the tables and all the data. So when a troubleshooting occurs, or you have to do it, you first go to the trace ID table, then get the associated span, and then look the span details. And if you have to do an error investigation, you can directly look up to the special shard instead of going to the whole table. This helps you increase the query efficiency by 50 to 100x. Now, for a long-term cost management, how can you build your storage, or how can you build this cost-efficient storage? So for that, you can have a tiered architecture. You can have 3 main levels, like hot storage for the recent data. It is typically for 0 to 7 days, and we use high-performance SSDs to store that. Then you have warm storage, which is typically 8 to 30 days. You store intermediate data here, and we store that in cost-effective HDDs. Then the last is cold storage, where we store the historical data, which is more than the 30 days. And you use object stores here, like S3, GCS. And then again, you have the special shard for the errors and the slow span. So now, now you can have automated data migration at the regular interval. So you go through the data as the data ages, and then you find and extract the error and the slow spans, and then copy them to the special shards for easy access, and then move the regular data to the architecture based on the age. So most of the system has 1% of errors of the total volume of trace. So, and these are the errors that you need at the time when something breaks, you need them the most. So just optimizing this 1% of data, you can have a better visibility to your system. So special shards are small and cost-effective, and they can provide you a complete visibility into your system. Now let's talk about the key takeaways from this whole journey. So first, the tracing is the best debugging tool. It provides the highest fidelity signals to finding the root cause. You get a complete picture of what is happening, and you find the root cause, and you don't have to spend hours on to looking or guessing what is happening. Next, most of the problems are coming from sampling because we have a huge amount of data and we try to do sampling, which leads to create blind spots and create a debugging nightmare. But the good thing is we have a solution. We can achieve 100% sampling with right techniques like columnar storage, smart sharding, and efficient indexing. Fourth, so this doesn't help only in debugging, but it also reduces the mean time to resolution, lower your storage cost, and improve the query efficiency, and it provides you a better observability into the system. Thank you all.